Hello everyone, this is Lauren. I'm an alto in Helios. I'm the blonde one that looks like Chelsea but is not Chelsea. And I want to talk to you a little bit about the physics of music today. I accidentally took too much physics in college, so now I know some things that I want to share with you. So, when we think about sound, what is sound? Sound is the disturbance of air particles. So we have our particles, and when they get hit by a sound wave, they're going to start moving back and forth in their own little space. So if this particle gets hit, it's going to be moving kind of like this. Up, down, up, down, up, down. And we can plot our displacement as a function of time. So we have up, down, as the particle is vibrating back and forth. And so we want to be able to determine how to distinguish different frequencies of movement. So this is 1.75 cycles per second, and cycles per second is the same thing as hertz, so that's 1.75 hertz. We can have something called low frequency, which is where we don't have that many cycles per second. So here we're moving very slowly. So this is the equivalent of moving kind of like this, where we really don't have that many cycles per second. So this is low. We can also have something moving at a high frequency, which would be something very quickly like this. And we would model that as having a lot of cycles per second. So this is high frequency. Now, how does this frequency relate to notes in music? So frequency are correlated with the notes in a scale. So frequency corresponds to pitch. Now, most of you had probably heard at some point that an A440 is an A note and represents a tone of 40 hertz. But what are the relationships between this and our own brains? So in our ears, we have little hairs that act as sensors that pick up different frequencies. And they fire a signal to the brain that says that I'm hearing a certain frequency. So our brains actually work by selecting things as a frequency and then combining all frequencies into a larger sound. So this might be our 440 hertz hair, this might be our 220 hertz hair. Speaking of 220 hertz, we want to also understand how this maps to our own system. So in our system of notes, we have A sharp, all the way through G sharp. So we have 12 notes in one octave. And going from the lowest A to the highest A is a multiplication of 2 of the frequency. So we want to know what we multiply by to get the next note. So A times something would be equal to A sharp. A sharp times something would be equal to B. B times something would be equal to C. Because we have 12 steps, and we know that a whole octave is 2 times, we have x to the 12th equals 2, and then we can solve for our x. So 1.0569 is the ratio from one note to the next note in frequency. So I wrote out some frequencies here. We have 220 and 440, so you can see that it's doubled. And you can see that, say we want to look at B. B is 246 hertz, and if we multiply that by 1.05, we get 261, which is the next half step up. You can also see, though, that this octave is not just for A's, it's for any note. So you can see here our D sharp is 311 hertz, and the D sharp an octave higher is 622 hertz, which is double. And then same thing for E, we have 330 hertz, next octave up is 660 hertz, which is also double. So that's all for today. I hope you all are enjoying some time now, but I miss singing with you, and I look forward to being back. See you later. Bye.